Welcome back to Meaning from Data, Statistics Made Clear. In this lecture, we begin a series of 4 lectures concerning how we extract meaning from data when we know all the data of the population that we're interested in. And then in later lectures, 8 through 12, we'll consider the question of how to infer information about the whole set of the population when we just have information about some of the members of the population, a sample. So, to describe a set of data, we have to confront the challenge of taking a list of numbers and putting some structure on them through which we can garner meaning. So, as we begin in this lecture, we're going to take the principles for organizing, describing, and summarizing data, and when we have all the data in the whole population, and figuring out how to look at issues of it. And one of the basic features of a set of data that we'd like to describe is how closely the numbers in that set of data are clustered together, or how widely they're spread apart, how dispersed they are. And this measure of the variability of the data is going to be accomplished by developing a few different concepts of dispersion or spread. And so in this lecture, the goal of this lecture is to define and explore the standard deviation. So we'll define that later in the lecture. And that's a measure of how widely data from a data set are dispersed. So the various methods of, we'll start by, first of all, when we're talking about dispersion, we're talking about dispersion from something, and that's a central value. And so what we're going to do is talk first about some of the measures of central tendency that we've already, in fact, met before. So the first thing that we're going to do is review the 2 one-number summaries of data that we already met in Lecture 2, namely the mean and the median. The mean and the median, although they both measure central tendency, they're both one-number summaries, notice that neither one of them speaks to the issue of how dispersed the data are. So let's first of all review the mean and the median. The median, remember, is the number that you get if you list all of the data and you take the number that's halfway up that list. So that's the median. And it represents, in some sense, the data by a single number. And notice that the median is not affected by outliers. Outliers meaning values that are really extreme. Because if you have a list of numbers, and if this number is in the center, well, if you change the biggest number to be much, 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 much bigger, it doesn't affect that number at all. So the median is not affected by outliers at all. Okay? But the mean, on the other hand, is another measure of center, and it's the most common one, at least when you think of the word average, you probably are thinking of the mean. The mean, remember, is the sum of the data divided by the number of elements in the data. So here is the actual equation for the mean. And it's often represented, by the way, by x with a bar over it, or by the Greek letter mu, depending on the context, which we'll talk about later. So the x bar, which is the mean, is the sum of all of the data divided by the number of data points that you have. So if you have salary data about how much salary each of 100 people makes in a company, you would add up those 100 salary numbers and divide by 100 to get the mean. And there's a fancy notation for this, which is this capital letter sigma, I going from 1 to n of x sub I. The sigma, being the letter S, really stands for sum. It means add up. So it adds up. I going from 1 to n means that you take this little letter I and make it a 1, then a 2, then a 3, all the way up to n. So if we had the salaries would be I going from 1 to 100 of x sub 1, x sub I, and then that would be shorthand for this equation right here. So that's just a little notational thing, and don't worry about it. But the mean has a physical property that is rather interesting, and that is can be described by putting a histogram of the data and then taking this physical action, which I'll describe. Here's a histogram of a collection of salaries from a given company. And you can see that the histogram, the heights of each of these bars indicate how many of the people make a salary between, in this case, $60,000 and $70,000. And so this is 2 people make that salary, or 3. And so on. So this is a histogram of the salary data. The mean is the place that you would put a fulcrum if you thought of this as a teeter-totter. So the mean is the place at which the data balance. You see? So the data balance, if in this case the mean is $44,000, so if we put the fulcrum right here, the data would balance. Okay? Now notice that if you have a teeter-totter, I mean in real life you have a teeter-totter, and by the way, I have to say specifically that the teeter-totter that we're thinking of doesn't weigh anything itself. That is, the board doesn't weigh anything. And that what we're really doing is just putting one, say, coin at each place where each datum is. And you just lay it on the board that is marked by the numbers. And so you could have a stack of 3 if 3 of them have the same value here, and a stack of 2. Well, notice from your own experience of teeter-totters that if you put the little kid way out on the teeter-totter, it'll balance a heavier person that's nearer by. The effect of that is that that's a physical manifestation of the fact that the mean is susceptible to being strongly influenced by outliers. If you put a high number in, there's a big effect on the mean. So this, by the way, is a histogram of exactly the same data set that we had before. And that's interesting just in its own right. Notice that the only thing that's happened is that the x-axis here, the horizontal axis, has changed where this is now $100,000 right here. So all the data are crammed together. So here we go. Here I went back. There are the same data. Notice this one goes from $10,000 up to $90,000. And then in this one, it's exactly the same thing, except they're all crammed together. The reason I want to do this is I want to illustrate an outlier by adding one more value way out here. You see this? $1 million salary. The way to think of this, by the way, is that this might be a company, and most people make amounts of money that have a range between, in this case, the $20,000 and $90,000, but then we've got the CEO of the company who's making $1 million. So this is an example where the effect of that one salary, including that CEO salary, the effect is that the mean now is $64,000, whereas without the salary of the CEO, it was only $44,000. So that one salary change made a big impact on the mean. So the mean, then, the way this is phrased is that the mean is susceptible to the influence of outliers. So a single number summary, in order to decide what single number summary that we want to use, if any, we need to see its properties. And one thing that we've seen is that one of the properties is that outliers have a big effect on the mean, but don't have a big effect on the median, and that can influence it. And so let me give some examples. A single number summary, it would not be useful in the following situation. Suppose a farmer has 100 chickens and 100 cows. Then you could say that the mean number of legs per animal is 3. That's true, but probably not a useful thing. It loses some of the information about the animals. Okay, so here's an example. Suppose you looked at houses that were selling in a certain area, and you were thinking about getting a sense of the prices of houses in that area, and you found that the median was $191,000. That probably is a better measure of central tendency of house sale prices than the mean. Because often if you have, say, one house that's sold for several $1 million, it could have a big effect on the mean of the housing prices, and it would give you a distorted view of what the, so to speak, average or typical house was selling for. So in that case, you would say the median was a better thing to use. We saw the salaries at a company where, once again, if you were thinking of being employed at the company, probably looking at the median salary would be more representative of what you're likely to make than looking at the mean salary, which included an outlier. If you look at an example like the heights of adult men in the United States, where the graph has this nice symmetric distribution about a center value, the mean is a very good way to summarize that kind of data set. But none of these things talks about the distribution of the data. So, and the distribution of the data is important. That is not only where the center is, but how spread out those data are is an important issue. For example, and here's a case we met already before, was the case of the distributions of the batting averages of batters in the year 2000 versus the year 1920. In the year 2000, the batting averages were more squished together. They were not as widely spread. That is to say, the people's batting averages were more similar to one another. There's less variation. From the 1920 batting averages, they were more spread out. In the lecture 16 on sports, where we asked the question, who is the best hitter in the history of baseball, it's going to be very important to realize what the significance is and the consequences of having the data spread out or more widely dispersed like they were in 1920 or closer together like they are in the year 2000, even though they have the same center. And one of the issues has to do with how likely are we to see a batter get a 400 batting average in a season in the future, and we'll see why it would be an unexpected occurrence in our lifetimes. But that's for lecture 16 to deal with. But it illustrates the idea that the dispersion of the data, the variety of the data, is an important thing for us to look at. So, because much of the information about a set of data is lost if we just look at the mean or the median to summarize it. Neither of these tells us how widely the data are dispersed. Now, we can look at some things to tell something about the dispersion, namely we can look at the maximum value of a data set and the minimum value. We can look at the quartiles of a data set. Those are all measures of dispersion that give us some sense of how dispersed the data are. And in this example, here is a collection of data that actually two sets of data, where here we have a lot of data in the center and then two collections of data that are to the sides. Whereas in the second data set, there's almost nothing in the center, but and much more data are on the two sides. Many more data points are on the two sides. Look what happens when we summarize that with a box plot. The box plot that we get are identical in those two cases, because the box plot is just telling us where the minimum value is, where the maximum value is, what the median is, and where the first and third quartiles are. And we chose these data sets to have exactly the same maximum as one another, a maximum as one another, minimum as one another, and the quartiles in both cases lay at exactly the same places. So this illustrates the idea that the box plot strategy for talking about dispersion misses some of the main character of the data set. Namely, this data set, number 2, the difference between the values is bigger than, on average, than the data set for data 1, because a lot of the data in data set 1 are all centered at the same place. So our goal then is to try to actually find a way to measure this dispersion of data. Now, a histogram, by the way, does give us a better illustration of how it is that the data are spread out, because it shows where every place is on the data. But what a histogram does not do is give us a single numerical number that tells us how widely spaced data are. So that's the challenge that we now turn to. We now turn to the challenge of describing some numerical measures of dispersion, how widely spaced, how spread out data are. Now, let's think about this. Let's suppose, all these things are made by humans, by the way, of course, by just thinking about what we're trying to do and then making a definition that tries to capture what we're after. So in the case of trying to measure how spread out data are, what is sort of a natural way to do that? So let's just think for a minute. If you have a collection of data, and think of it like, say, the salaries at a company, how are you going to measure how widely spread those data are? Well, a natural way, I would think the very first way that you'd think of doing this would be to say, let's take the mean value, the center value, the mean of the salaries, and then for every salary, let's just see how far away it is from the mean. You follow me? Does that make sense? You take the mean and you just say how far it is for each single salary. You say, well, this one is quite a bit lower. This one's quite a bit higher. Now, by the way, we should take the absolute value. So we're talking about the distance away. We don't want them to cancel out because we're trying to measure how far away they are from the mean. So we take their absolute value, and we could, a measure, a numerical measure of how far they are from the mean would be to say, what's the mean of their distances from the mean? You follow me? What's the mean of the distances away from the mean? So let's look at this example. Here's an example that has just 4 data points. These numbers are -6, -4, 4, and 6. Very simple set of 4 data points. The mean of these 4 data points is 0. I chose them to balance at 0. You can see that there's a -4 and a +4, -6 and a +6. They're going to balance at 0. So 0 is the mean, and the average deviation from the mean, that is the average distance away from the mean, is what? Well, the 4 values, the -6 is 6 away, -4 is 4 away, +4 is 4 away from the mean, which is 0. 6 is 6 away, dividing by 4, we get 5. That is the average distance away from the mean. And it seems like a good measure of dispersion. However, it turns out that this measure of dispersion is not the most commonly used measure of dispersion. The most commonly discussed measure of dispersion is called the standard deviation. And it's a little more complicated than this, and I'll tell you why in a few minutes. So our goal is to find a numerical measure of how spread out the data are so that you get a bigger number if they're more spread out and a smaller number if they're more clustered together. And the standard deviation accomplishes that, just as, by the way, the average deviation accomplished it. But let me first of all tell you how to get the standard deviation, and then we'll discuss why it's the measure that is most commonly used. So here's the definition of the standard deviation. The first thing that we do is we go through our collection of data, and for each datum, we look at the difference between it and the mean. Mu is the mean, by the way. So in this fancy formula, mu is the mean and xi are the different data values in our collection. So for example, if we're talking about salary, for each salary you take the difference between the salary and the average salary, the mean salary, and then square it. So you square the difference from the mean and add up all of those squared differences from the mean value, and then take the mean of those, that is, divide by n. So this number, which is designated sigma squared, is called the variance. This value is the average squared distance away from the mean. So it's exactly like the average deviation that we talked about before, except that we're squaring each of those differences. Square each difference, and then just divide, take the mean of those squared differences. And the square root of that is called the standard deviation. So the standard deviation, we do some squaring, then add up the squaring numbers, and then take the square root to get the standard deviation. And you can see that it's basically just as before, a measure of how far away a typical value is from the mean. Or maybe I shouldn't say a typical value. What I should say, it's the mean of the square root of the squared sum of the squared distances from the mean. So this is the definition of the standard deviation, and let's just do an example to ground it in reality here. Suppose we take our same collection of 4 numbers, so -6, -4, +4, +6, and once again the mean of these numbers is 0. They balance at 0 if we put them on a teeter-totter. And let's go ahead and compute the standard deviation. The average deviation, which we did before, remember, was 5. And the standard deviation, remember what we do, we take the square of each distance from the mean. So we take 6 squared, for our -6, we square that and get 6 squared, 4 squared, 4 squared, 6 squared, and add up those squares. By the way, squares are always positive numbers. That's one reason to square, is that you don't have to worry about absolute value signs. So you square it, divide by 4, and then take the square root. And we get 5.1, slightly bigger than the average deviation. And that's typical, that you will get a number that's slightly bigger than just taking the average distance of the points to the mean. And by the way, just to remind you of the terminology, this number before we took the square root, whose value is 26, is called the variance. So it's the mean of the square distances from the mean. So it's the variance. So the standard deviation, and by the way, we're using the letters that are typical, customarily used for standard deviation, sigma for the standard deviation, or S, sigma squared or S squared for the variance. Now I have to say something now so that to avoid getting lots of emails telling me why I'm wrong on the definition of the standard deviation. Very often, the definition of the standard deviation will have a division by n-1 for the variance and the standard deviation instead of n. In other words, that you take the sum of the squared differences from the mean, add them up, and instead of dividing by n, divide by n-1. That is the correct definition when you're taking a sample of a population. If you're looking at the entire population, which is what we're concerned with in this lecture, where we know all of the data from the population, then it's appropriate to divide by n. And in a future lecture, we'll see what the difference is and why we divide by n-1 if we're taking a sample. You may wonder why it is that we choose to use the standard deviation rather than the average deviation. Remember that the average deviation was very simple. The simple idea, you just took the average distance from the mean to each data point and took the average. And that would say how far on average the data are spread from the mean. Why do we need to go to this trouble of squaring the difference between the mean and each data point, adding them up, dividing by n to get the variance, and taking the square root? Why go to all that trouble? Well, one of the answers is that if we take just the average distance to the mean, notice that it has the following property, that if we look at our data set, -6, -4, 4, 6, if you took the average distance from 0, the mean, you would get 5. But look what happens if you take the average distance from the point 1. You see what happens? The -6 gives us 7, the -4 gives 5, that's 12 altogether, and then each of the upper ones is reduced by 1 because we're at 1 instead of 0. So the 4 just gives a distance of 3, and the 6 just gives a distance of 5, so that's 8 more. So you notice that the total, 12 plus 8, is 20 again, which divided by the 4 data points, 4, gives an average value again of 5. So we got the same average distance from 0 as we got average distance from 1. or in fact 2, or -1, or any number between -4 and 4, in fact, would always give us that same average distance. So taking the average deviation doesn't help us to find the unique mean, whereas the standard deviation has the property that it minimizes the deviation. That is, if you take the mean value and you take the sum of the square distances from the mean, and you take that mean of those, you divide by n to get the variance, and you take the square root, that number is minimized by choosing the mean as the value from which you're taking these differences and squaring them. So, and I wanted to demonstrate this by some rather complicated looking work. If we choose a central value and we think of it as m, and we think about taking the sum of the squares of the distances from m to each of our data points in turn, and then we add up those squares, our goal is to say, what number m will make that number the minimum among all possible m's? And we're going to find out that it's actually the mean. And this fancy work here is trying to minimize the sum of the square distances, and all we do is we take this sum of the square distances, multiply out that square by the algebra that you may or may not remember from high school, and then what we do is I'll tell you, the reason I'm doing this is I'm demonstrating that calculus actually plays a role in statistics, and you don't have to follow any of this. So I'm just going to do it very quickly. Taking the derivative gives us this sum. If we're trying to maximize a value in calculus, what we do is we set the derivative equal to 0, which occurs when this equation is true. Solving for m, we see that we get exactly the mean. So this is an example where calculus actually shows us that the mean has that special value of being the only place where the sum of the square distances is minimized. So it's unique. And that's one reason for using, it's a technical reason, but it's a reason for using, one of the reasons for using the standard deviation and variance instead of just the average distance. That's an aside, and you can safely ignore it. Let me just point out that the salaries of a company, the ones that were less than $100,000, we see that the standard deviation is $19,000. So that's a measure of roughly how far a typical salary in that range differs from the mean, $19,000. But look and see what happens when we add the CEO's salary. So we'll go through this computation where you have the CEO making $1 million. What happens? The mean goes up to $64,000, and the standard deviation jumps to $138,000. So it's saying that the standard deviation is far higher than it was before. So the standard deviation is susceptible to a strong influence by an outlier. Well, in this lecture, then, what we have discussed is the ways of measuring dispersions and difference of dispersions. And we had the measure of the standard deviation, which then can be used. And the way we would use it is to compare sets of data. For example, we might want to compare the salary distributions at companies in Japan compared to the way salaries are distributed in the United States. And we would find that the standard deviation of salaries in companies in the United States is much smaller than the standard deviation, in Japan, is much smaller than typical ones in the United States. Their CEOs' salaries tend to be lower, and that's one thing that the standard deviation records. We saw different measures of looking at dispersion. One was the 5-number summary, the minimum, the maximum, first quartile, median, and third quartile. And we saw that the box plots that are associated with that give us some sense of the dispersion of data, but it didn't give us a numerical measure, and it didn't follow the whole distribution. The standard deviation is a numerical measure of roughly how far the data are on average from the mean. So this was one of the basic concepts in statistics. And in the next lecture, in this lecture, we were talking about, in our triumvirate of shape, center, and spread, in this lecture we were talking about spread. and also center. In the next lecture, we're going to take on the challenge of shape. I look forward to seeing you then.